In this video, we're going to talk about demonstrating realistic frontogenesis using semi-geostrophic processes to do so. What I've already illustrated for you here is what we're going to begin with. And so we are essentially looking at a 700 millibar confluent flow pattern. And so here we have streamlines that are indicating the confluent flow. We have our potential temperature in red, and that the wind is maximized here over on the right-hand side in our typical X and Y coordinates. And so this is initial 700 confluent flow. And where we're going to go now is we are going to ask, well, how does this change a cross-section as we go through time? And so we're going to first initially draw out our initial cross-section and then ask what happens just after this initial 700 millibar confluent flow. So keep this picture in mind as we go ahead and begin our process of thinking about what does our cross-section look like. And so let's go ahead and draw ourselves a nice cross-section. And we are going to be in our Y and P increasing as we come to the surface. And where we can think about this, we can draw in where this cross-section might be. And so we can think that our cross-section might be along this line, such that we can say we're to the south on this end, to the north on this end for our purposes. Doing so, we can draw in our tilted isentropes. And so remember, our isentropes are always tilted towards the cold air. So that would be to the north in the northern hemisphere. And we can draw out our various isentropes. So here we have our theta minus delta theta, theta minus 2 delta theta. And then on the other side, theta plus delta theta, theta plus 2 delta theta. And so initially, we know that the atmosphere is still in thermal wind balance. And so we can draw in some perspective height contours. And so, for example, at 700 millibars, we know that we would have higher heights where it's warmer and lower heights where it's colder. And so this might be an example of our 700 millibar surface. And we know from our 700 confluent pattern, we know that we have air that is coming out of the page in this case. And so we can signify that by our geostrophic wind here associated with UG, where our dot with a circle is out of the page. Similarly, at lower levels, we can draw in, say, a 900 millibar surface, which may not have much change in slope, but may just increase slightly towards the cold air, as we know that denser cold air and higher pressure often resides there. And so here, if the atmosphere is in geostrophic balance, we might have a slight wind then out of the page, where X with the circle is, not out of the page. Misspoke there. That would in fact be into the page, or into the screen as the case may be. And so initially, we are going to say that everywhere our wind vector, our total wind vector, is equal to just the geostrophic wind everywhere. And remember, when we're developing this idea of A-geostrophic circulations, we develop A-geostrophic circulations. Okay, and so initially, if we're looking at just our V components here, we know that with our confluent flow above, we have our VGs pointing in. Now this is just the component VG as opposed to the total wind VG. And again, we are here at time t equals T naught. And so we want to ask ourselves, what would happen immediately after this confluent flow starts? And so if we've come back up here to our image, what is going to happen to our gradient in temperature, in potential temperature here, as a result of our black line confluent flow? Thinking back even just to our kinematic structure of frontogenesis, what should happen? That's right. Initially, what should happen is we should get cold air advection on the cold side and warm air advection on the warm side, thus increasing the strength of the magnitude of our gradient in potential temperature. And if the atmosphere is in hydrostatic balance and thus thermal wind balance, what should happen to the geopotential heights as a result? That's right, they're going to change. And so we're going to get an initial tightening of our temperature gradient. And so let's go ahead and draw our new cross section here. Again, in our Y, P increasing towards the ground, our south, our north, we should get here an increased strength in our potential temperature gradient. Now, it may not be a whole lot here. Oops, that should be minus delta theta. But it is an increase. And so we'll quickly get in here, theta plus delta theta, and theta plus 2 delta theta. And so what we want to draw in now are some responses of our heights due to this increase in the gradient of our temperature, such that primarily it's going to affect our 700 millibar surface, where we should have more slope, and we may not have, again, much slope to our 900 hectopascal surface. And so we want to first consider only these changes in our geopotential heights, and thus changes to the geostrophic wind. And so recall initially, right, we said that V was equal to VG everywhere. Now we're going to ask ourselves, well, what is going to happen as a result of the changes to our geopotential heights to our geostrophic wind that could cause changes and create a geostrophic flow? And so, again, our geostrophic height change is going to cause changes to our geostrophic wind. So if we recall, the component UG of our geostrophic wind is equal to minus G over F times dz dy. If our gradient in the height increases, we know that our UG component should also increase. And so we can start assessing at different levels what's going to happen as a result of this change to the geostrophic wind. And so specifically, we want to start at low levels. And so at low levels, we know that in general, we're going to have very little change, but at our time t equals t naught plus delta t, we are going to have a dz dy that is greater than 0, such that our UG now at our low at time t plus delta t is going to be less than our UG at time t naught. It's going to be even more negative. Okay, at upper levels, our dz dy is going to be less than 0, such that UG above at our time t plus delta t will be greater than our UG at time 0. And so this is going to be even more positive, such that from our original piece to now, we know that both our out of the board aloft UG and our in to the board UG below are going to be greater than what they were originally. And so this then leads us to be able to assess our understanding of the A-geostrophic flow that's going to begin with this particular setup. And so below, or at our low levels, we are going to have we want to assess our A-geostrophic flow at our below levels. And so we know that U minus our UG, so our initial U minus our current UG, so this is going to be less than 0, and this is going to be even more less than 0, will make this whole term greater than 0, such that we're going to induce A-geostrophic flow from the north. And we know that because we can relate our dV/dt term equal to minus F times UAG low, such that VAG low will be less than 0, or from the north. And above, we are going to get a UAG above equaling U minus UG, which in this case is going to be greater than 0, and then much, much greater than 0 at our new time, so that it's going to be less than 0, such that our dV/dt equaling minus FUAG above is going to lead to our VAG above to be greater than 0, or from the south. So what does this mean for our picture? Above, our A-geostrophic flow is going to be from the south. And so let's go ahead and draw our VAG from the south. And then below, it's going to be from the north, such that it's going to be greater than and less than outside of where we see our strongest temperature gradients, such that we are beginning to see the semblance of our circulation going on. And we can complete our circulation from knowing that really our divergence is really acting only on the A-geostrophic portions of the wind, such that we have DUAG, dx plus dVAG, dy. And so then we complete our circulations by having rising motion out ahead of our fronts, sinking motion behind our fronts. And we get essentially this area of convergence occurring along the angle of our initial temperature gradient. And so we see from this initial small confluent flow, remember starting up here, we have our 700 millibar confluent flow with our initial cross-section here. With that initial confluence strengthening the temperature gradient, giving us changes in our geostrophic height, this immediately leads to the beginning of our A-geostrophic circulation. But this isn't it. It turns out that not only can we consider the changes due to the temperature, and thus the geopotential heights, but our momentum advection also plays a role here. And it turns out that from our momentum advection, we are going to get the same result. And so below, we are going to have U greater than UG immediately. such that our dv dt is going to be less than 0, such that our v ag low is going to be less than 0, which is the same sign as what we got with our height changes above. And so we're going to have increased A-geostrophic flow from the north. Again, for above, we will immediately have U less than UG immediately, such that dv dt will be greater than 0, and our VAG above will be greater than 0. And so these are the same sign as the changes in geostrophic height. So the net effect is being double of the individual geostrophic advection for both the top and the bottom for temperature and momentum, meaning we really accelerate the generation of this circulation. And so our A-geostrophic circulation leads to sinking motion on the cold side and rising motion on the warm side, which we can see illustrated here in our figure. And we get areas of convergence and divergence associated with this pattern. And we get convergence where we have the slowing of our A-geostrophic wind, and divergence in our other locations. And so we get this convergence axis between the lower left and the upper right, which corresponds to our region of enhanced vorticity generation, and thus then enhanced gradients in potential temperature. This is a direct circulation that sets up in our frontal zone and begins to tilt our isotherms in the horizontal, while also increasing the horizontal gradient to potential temperature along the zone of convergence and tilting everything towards cold air, such that at a later time, we now get our tilted aspect of our isentropes to be more realistic and only have zones of static stability and cyclonic rotation and we've got our full-on circulation associated with our front here, this direct circulation. And it's this direct circulation that is giving us our front in a realistic time frame with only cyclonic motion, and thus these A-geostrophic motions are acting to force the actual winds towards maintaining geostrophic balance and thermal wind balance. So in essence, what's going on here is that when we create stronger temperature gradients, the atmosphere is responding to undo those temperature gradients, i.e. a direct circulation. To then undo that and geostrophically adjust the atmosphere. And so these motions accelerate the process of producing a front in a realistic time frame. If we didn't have some of these A-geostrophic components, specifically here this second piece about our momentum advection with our A-geostrophic flow, we would not be able to get our frontogenesis in a realistic amount of time, which is what we were seeing with our QG equations. And so that's why we need the geostrophic momentum approximations to use to generate our semi-geostrophic theory to then be able to describe why we get our frontogenesis in a realistic amount of time with the appropriate elements of just static stability within our fronts, only cyclonic wind shifts, and in a reasonable amount of time. And that's how we can get fronts in realistic amount of time. Hope this helps explains a little bit about fronts and the circulations associated with them. Thanks for watching.